Have you ever looked at a complex operational amplifier circuit and wondered how engineers quickly analyze its behavior? Virtual ground is a fundamental concept that dramatically simplifies the analysis of ideal operational amplifier circuits, particularly when deriving the gain of an inverting amplifier configuration. It means we can treat the inverting input terminal of the amplifier as if it were directly connected to a ground reference, even when it is not physically wired there. This powerful simplification arises from two key characteristics of an ideal operational amplifier and the application of negative feedback. First, an ideal operational amplifier possesses infinite open-loop gain, meaning even a tiny voltage difference between its input terminals would produce an enormous output. Second, with negative feedback, the output adjusts itself to essentially eliminate this voltage difference, effectively forcing the voltage between the inverting and non-inverting inputs to be zero. Therefore, if the non-inverting input is connected to actual ground, which is typically 0 volts, the inverting input must also be at 0 volts due to this nulling action. This condition, where a node is at ground potential without a direct ground connection, is what we call virtual ground. Applying virtual ground to derive the inverting amplifier gain begins by assuming the inverting input is at 0 volts. We then use Kirchhoff's current law at this virtual ground node, stating that the sum of currents entering and leaving the node must be 0. For an inverting amplifier, this means the current flowing through the input resistor must equal the current flowing through the feedback resistor, since no current can enter the ideal operational amplifier's input terminals. By expressing these currents using Ohm's law, relating them to the input voltage, output voltage, and respective resistance values, we can then easily solve for the output voltage in terms of the input voltage and the resistor ratio. This elegantly leads to the well-known inverting gain formula of minus RF over RIN, where RF is the feedback resistance and RIN is the input resistance. Understanding the virtual ground concept is a true cornerstone for analyzing a wide array of operational amplifier circuits, not just the inverting configuration. It provides a direct and efficient pathway to understanding complex circuit behaviors and empowers you to quickly grasp the core functionality without getting bogged down in intricate calculations. This analytical shortcut is why it is so widely taught and applied in electrical engineering. In essence, virtual ground demystifies the operational amplifier, transforming what might seem like a tricky derivation into a straightforward application of fundamental circuit laws. It provides a clear, simplified model that allows engineers to quickly determine how these versatile devices amplify and process signals, offering a solid foundation for designing and understanding more complex analog systems.